Hi, my name is Abe Kazemzadeh, and I will be presenting a paper entitled BERT-Assisted Semantic Annotation Correction for Emotion-Related Questions. First, let's look at the overview and the big picture. So the big picture is the automation of the annotation process. But this paper is looking at a specific focal issue, namely automatically correcting annotation errors. And the way that we're going to do this is with the BERT neural language model fine-tuned using the paraphrase task. And the data we'll use is dialogue data from the Emotion 20 Questions game, where players ask each other questions about emotions. We'll talk about this later. The result we found is that BERT is able to identify annotation issues in held-out data. And the novelty is using BERT for annotation correction rather than focusing on purely prediction. In traditional annotation, we have this top picture where the human annotator will annotate training data, we'll train a model, and apply that to held-out test data. Here we have a similar picture, but with BERT, we have a pre-trained model, so a model that has been trained on a large amount of general language data like web crawl data, and then we use domain-specific data to fine-tune that pre-trained model, and then we apply that to unseen test data, and we get a prediction on that unseen test data, and the results are fed back to the annotator, so we call that the assisted annotator, who can decide to correct the annotations. So we're motivated by, of course, correcting annotations, and like I said, this is one form of automated annotation feedback. One reason you may want to consider this is if you have limited resources. For example, when inter-annotator agreement is not possible, then there's no way to determine whether the annotations are actually correct or consistent or not. This will also be useful in cases where there are difficult annotation tasks. In this case, it's assigning semantic labels to dialogue utterances. And finally, I had the aha moment when I noticed that the annotation errors, I noticed annotation errors when evaluating BERT's prediction. So I was looking at using BERT for another task, but I noticed that BERT was identifying places where I made annotation errors. Okay, let's look at the background material. First of all, let's look at this bigger area of annotation automation, so different approaches and factors. One approach is pre-annotation, where you apply a machine learning model that has been trained on existing data to the data that you're interested in. So that's called transfer learning. There's also this approach, incremental or online learning, where you train the model concurrently while annotating. And also active learning, where the system will automatically suggest the most informative training examples, so you don't annotate unnecessary training data. And some factors with annotation automation is task complexity and experimental control. So you can have very simple annotation tasks, labeling something like hot dog, not hot dog, or something that's more complex like semantic predicate logic kind of annotations, like we'll see. And another factor is experimental control. So whether the annotation and the data is in a controlled environment versus in the wild or in a kind of pervasive computing context. Next, BERT, we'll talk about the precise models we'll use, but more generally, BERT stands for bidirectional encoder representation from transformers. If you haven't heard of it, it is a landmark development in natural language processing, or NLP, developed by Google. It's a neural language model And as a language model, its basic task is learning word occurrences, so predicting masked words, held out words in a sentence, and predicting the next sentence in a series of two sentences. And that is the way that it is pre-trained. And once it's pre-trained, it has parameters in its neural model that form a representation of linguistic information that can be used for many tasks. One of those tasks is the paraphrase task, which will take two sentences as input and actually combines it together into a single input and tries to predict whether that two-sentence pair are paraphrases of each other or not. So it's an interesting way to formulate this somewhat complex task into a binary classification task. So the two sentences are encoded by first prepending a classification token, then the sentence 1 tokens, a separator token, and the sentence 2 tokens. Comparing sentences in this way offers a way to evaluate semantic annotations. So if two sentences share the same semantic annotation, then they should be considered paraphrases by BERT. And in our case, we'll see the examples of the semantic annotations, but we'll just look at the simple string matching as testing the equality of the annotations, and we'll see that that actually leads to a couple annotation issues. Okay, the data that we're looking at is from Emotion 20 Questions. It's a dyadic or two-person natural language dialogue game where one player picks the emotion word and the other player tries to guess that emotion word in 20 or fewer questions. The question-answer pairs form a description of the emotion word, and our previous work involved creating an automated agent to play the question-asking role. So it used the human-human data to learn the question ordering and likelihoods in this following way. So the probability of seeing a question-answer pair given an emotion, and that would be inverted using Bayesian statistics to find the probability of the emotion given question-answer pairs. The questioner role is a lot easier to automate than the other role, the answerer role, because the input to the questioner role is yes-no type answers. It's quite limited. The answerer role is more difficult. Its input is any question. And so that was the context of us looking at BERT and this paraphrase task, because we needed to compare the input questions to the questions seen in the training data. And so it was kind of just that aha moment that led us to look at how BERT could be used for annotation correction. Here's an example of a dialogue in the Emotion 20 Questions game. This is actually the automated agent because it's a little bit, there's less small talk, so it's shorter. You can see that the user picks an emotion word, the agent asks several questions, and then eventually guesses correctly, relaxation. These strings here are examples of the semantic annotation. So they are a kind of predicate logic case where you can see this cause has two arguments, nothing, empty set, and then E stands for the emotion. And so these two pairs of dialogue utterances would be paraphrases of each other because they have the same semantic annotation. And similarly for these two, these two, and these two. Okay, so that's a taste of the data. Let's look at the kind of amount of data and how we trained the model. So we had 110 human-human Emotion 20 Questions games with 25 participants. That was about 1,200 annotated question turns and 700 unique annotations. Most of those annotations were actually hapaxes, so they were only seen one time, and you need two annotations to do the paraphrase task. So we excluded those hapaxes, leaving 543 questions remaining with 147 unique annotations. This doesn't seem like a lot, but the paraphrase task operates on sentence pairs. So there's a combinatorial expansion of the data, and this was annotated by just one PhD student. So keep that in mind, that we don't know the ground truth of the annotations because there hasn't been an inter-annotator agreement study. Okay, so we have these 543 questions after removing the single observation hapaxes. We expand these using n choose k permutations, where k is 2, so they're pairs. That results in nearly 300,000 paraphrase inputs. And so this is actually a significant amount of data, and it's more than the Microsoft Research Paraphrases dataset, which is one of the standard datasets in the paraphrase task. I'm going to go over the BERT training quickly because of concerns of time, and I'm also doing a demo, so that will look at the training more. But the main things to note are that we split the data into train, dev, and test sets, and the partitions have approximately the same proportion of positive and negative examples. So most of the data is not a paraphrase. So if you take any random pairing of two sentences, most likely it is not a paraphrase. We used the standard model, the base model. There's a large and a small, and base is kind of medium. And the training took about 50 minutes, so 25 minutes per batch. And so I'll go over that more in the demo. But the results are that we got very good accuracy, and the accuracy is kind of confirmed by the precision and recall statistics and F-score. But before we pat ourselves on the back about this, like I said, this paper isn't focusing on getting the best prediction performance, and we aren't really sure about whether those misclassifications are true misclassifications. We only know that BERT and the annotator disagree. So are those true misclassifications? That is, did BERT make the mistake, or are they annotation errors? Did the grad student make the mistake? And actually, BERT was smarter than the grad student, or more consistent than the grad student, let's put it that way. So we can divide the errors into 3 categories. Prediction errors, where BERT made the mistake, annotation errors, where the grad student annotator made the mistake, and data preparation errors, where the grad student's scripts made the mistake. Okay, so here's an example of prediction error. These are paraphrases. They're annotated as being the same semantic label, but BERT predicted them to be different. So you can see that die versus pass away, someone dear, someone close, there are some differences. So that's a kind of distant paraphrase. Here's a typo, jealousy is misspelt. Here's some case where the player was typing really quickly, didn't put spaces, so BERT got confused. You might think that that's asking a lot of BERT, but actually BERT has a fairly robust tokenizer that's not just looking at white space. So some of these are kind of more complex statements that are not syntactically paraphrases, but semantically they were labeled the same, so we would want them to be considered paraphrases. Another typo, etc. I'll go through these. So there were 16 prediction errors. I'm not including ones where they're just swapped in the paraphrase pairs. Okay, and some of these were actually non-native speakers, so you can see that the wording of some of these are different. And here, this one, BERT predicted it to be paraphrases, and they are very similar, but you can see that this is felt during betrayal, and this is besides betrayal, so kind of the opposite of this one, and although they are mentioning the same thing, so that was an interesting one. Okay, the annotation errors finally are here. So you can see here, this was actually annotated to be different, but BERT predicted them to be the same. And you can see here that it has some typos and everything, but BERT still predicted to be the same. And we can see that the annotation here is inconsistency. So it is using the predicate associated versus similar. And same with this one. You can see that the sentences are fairly different, but BERT actually predicted them the same. So BERT was correct, the annotator was wrong. And that was also a similar inconsistency in the predicates. And then this one is an inconsistency in the arguments. So that this is associated other person versus other people. Okay, finally, there's one data preparation error where this anonymization script replaced a user named test. This should have been the same meaning, but the anonymization script replaced user test by user 13. Okay, so for discussion and future work, we can see that BERT is useful because there's a low number of errors in the unseen test data. We don't have to go through many errors to see what are the annotation errors. But in principle, I think that any model's prediction errors could be indicators of problems with annotation. However, less performant models will take more work to separate the annotation issues from pure model-based prediction errors. And looking at the training data instead of the test data may be one approach for less performant models. So this is a batch approach, but an incremental or online approach could be very useful in the future. And instead of labeling the data using these semantic labels, it may be possible to start from paraphrases. Okay, so BERT is spectacular. It works on limited data. However, it has some trouble with typos or orthography. The paraphrase task is a clever way of extending data. However, it is not always symmetric. And this method provides a way to automatically verify annotations, but still requires a human in the loop. And I was a little bit joking about the grad student annotator. That was me when I was a PhD student. So this was unexpectedly fun to dust off my PhD dissertation. So I hope you can ask questions in the live talk. Thanks.